An advocate. Our association doesn't lobby. We're strictly a technical association, so we work closely not only with the contractors, but also VDOT, the other owners, to enhance material quality, paving quality of asphalt. So VDOT's the biggest customer that we work with for the industry. Smaller with localities, smaller with airport agencies, but it's mainly VDOT because that's what about 40 to 50% of the tonnage in the state is for VDOT. So, and most of the others will follow VDOT specs, so it's imperative that the specifications that's being followed are good specs, fair specs, and end up with the product that both are happy with at the end.
Okay. Well, Trenton, the first actual question that I'm going to ask you is the toughest, because I'm going to ask you to say and spell your name.
All right.
Give me your title, please.
Trenton Clark, TrentonClark, and I'm the Executive Vice President for the Virginia Asphalt Association.
Trenton, first question is why asphalt? Why use asphalt to pave roads?
Asphalt's the most affordable, reliable, and sustainable material available to owners to surface their pavements. So we can do it quickly, it can be done effectively, it can be done efficiently, and it allows us to provide for the traveling public, which is important, a smooth, long-lasting surface so we don't get in their way and interrupt them to have to do unnecessary maintenance, frequent maintenance.
Why is density such an important aspect of asphalt construction?
Well, it's interesting. Density is more of a function of what we're using it for. If we're doing a porous asphalt, density is not critical because we want drainage through the pavement. But for most of our uses where we're putting asphalt, density is critical to ensure that the water in the air doesn't go through the pavement structure. As the asphalt's exposed to water, as it's exposed to air, it leads to deterioration. So getting the proper amount of density to remove those interconnected air voids leads to a longer life. So density in and of itself, depending on the use, is critical to getting that life that's expected, the life that we're designing toward.
Well, talk about the relationship then between density and improved durability and performance.
Density and durability go hand in hand, but it starts all the way at the beginning with the mix design itself. You have to ensure that the mix that's being produced was designed in a way that has the ability to be durable. You can achieve high levels of density, but if the material itself isn't durable, then again, it's all lost. But if we start with a product that's got the proper amount of binder, it's got the proper amount of gradation, so when we take it out to the field, we get the compaction, we eliminate those interconnected air voids where we keep the water out, that we keep the air out, then we can enhance the durability of that material, enhance the durability of that road. We avoid rutting, we avoid cracking, and at the end, we get a long life surface. That means minimal times out into the road, closing it down to do maintenance for the traveling public, which again reduces their user cost.
So what are some critical things that DOTs need to consider for ensuring optimal density?
Few key factors are necessary for the DOT to get what they expect and what the industry wants to deliver. First, when they're looking at density, is having the specifications for the materials so that that material can achieve what's expected in the field. Most states, including our own, we're looking for right around 6, no more than 7% in-place air voids. But the mix is just one part of it. The roadway in which the material is being placed is critical. If the pavement is too deteriorated, it's not repaired properly before any type of paving operations, then achieving that density becomes much more of a challenge. Proper mixes being selected on a route is critical. Proper lift thickness is critical. There's many different aspects necessary to achieve that density, and it begins all the way from the mix design, the specs to be able to achieve it, to putting the mix on a road that's able to accept it to get the compaction necessary.
That's a great answer. And the next question, you've already talked on.
What was your address? It's
220 Oleander Court. But on the contractor side of the house, what are some critical things that contractors need to do in their construction process or practices to ensure there's good density?
Once you step away from the plant, so assuming everything is produced properly at the plant, everything's loaded out properly at the plant, the trucking is critical to ensure that you have a continuous flow of material to your paving train, that the temperatures are consistent, that as the mix goes through, whether it's a transfer device or directly into the paver, that process is continuous. Consistency from beginning to end is critical for that contractor to be successful. Constant speed of the paver, not changing, going faster and slower. If they started their operations with the paver screed on, the paver screed stays on. The auger operations are continually moving that material. And then the last thing is the rollers, that the rollers have, the contractor has the right rollers, has the right number of rollers, and adheres to the rolling passes and patterns necessary so that temperature and that mix is still elevated so they can get the density and keep moving down the road to get production. So it's consistency from the plant to that very finished roller to get the density, and they all have to work together. Any one of those stops or break down, then it makes it more of a challenge to be a consistent density in that mat.
Good, that's good. So talk about some ways to provide density quality assurance.
Quality assurance or quality control?
Well, I know there's two different things.
Yeah.
Quality assurance isn't that's really more on the agency side, is that right?
Well, quality assurance by federal law is the overall umbrella program. So you got the quality control that the contractor performs. You got the acceptance processes that can be done by the contractor or the agency. You have verification, you have independent assurance, but it all falls under the quality assurance umbrella. So it's a broad term that we use it interchangeably. That's why I say, what are we trying to refer to? Because it changes really how you answer the question.
So on maybe the government part, those specifications maybe or requirements, that would fall under quality assurance, wouldn't it?
The specifications covers your what you have to do from a quality control of the contractor, but also the acceptance of the product. So, if there's a minimum density of 93%, that's the acceptance. You accept it based on that criteria. The quality assurance is what are all those pieces that ultimately knows that you got, or the contractor achieves 93, and you make sure that they got 93.
How does, well, let me ask you this first.
All right.
What are some ways to measure density?
Measurement of density today, falls into really two categories. You got the non-destructive testing approach, whether it's from a nuclear gauge or a non-nuclear gauge, and then the destructive approach, taking cores and plugs out of the pavement. Both have their place. Both, it depends on the use of what materials you're using, the amount of checking that you want to do. The non-destructive devices work very well from a QC standpoint, from that quality control, from that contractor, ensuring that whether it's behind the screed or behind the different rollers, that they're achieving maximum density. The core still is while it's destructive, it's the one way that we're sure of what density is actually achieved. It's actually physically measuring it. New technologies that are coming on board that look promising, whether it's from using radar or other technologies will be the next big leap to make sure not only density is achieved in random locations, but really importantly, across the width of the mat and the length of the paving is how uniform is the rolling, how uniform is the temperatures that's coming out from behind the paver to ensure that we don't have isolated or even widespread failures because our testing's not so extensive that you can test every spot. It's just not practical. But the exciting thing is in the next 5 to 10 years, those tools that are available to measure and quantify density reliably are on the horizon. Is that Brett? Yep. All right.
Sorry about that. Some voices and coming across your audio. About temperature. Let's talk about how temperature affects density.
Today, that's a loaded question. It's not as much temperature itself as temperature differentials within the mat. Conventional wisdom was always hit it hot. To get density, it was a function of the mixes. With the inclusion of now the warm mix technologies, where we can get compaction because of the way the materials that we're using, whether they're the additives or the different types of chemicals that can be put in the mixes, allows us to get compaction at lower temperatures. The key is the uniformity. Is it uniform behind the screed as we're paving down the road to make sure that our roller patterns are set up to achieve uniform compaction across the width? One of the biggest challenges is again, consistency. If the mix is coming from the plant, going into the trucks, coming out, the screeds at different temperatures, mix is allowed to cool, the rollers and the paving trains separate. Anything that kills that or changes that consistency from which we set everything up impacts our density, and you see it in the numbers. Warm mix technologies have aided greatly in this to allow us to get better compaction at lower temperatures. But for a lot of the mixes that especially have lots of polymers in it and other types of additives, knowing that temperature, measuring that temperature, and keeping the rollers near that paving train is key to getting uniformity across the entire paving mat.
Let me ask you this. Are there changes to pavement design or asphalt mixture design that would make achieving density, achieving consistent density, easier for paving contractors?
Changes in pavement design itself? Two different things. For the pavement design, it's in putting structures in place and building layers that have enough rigidity so as you're laying the next lift on top of it that you have something to press against. That's key. So it's looking at the overall structure itself, where your stabilized layers come into play, how the subgrade will impact the ability to, again, compaction is pretty simple. You got to have a force pushing up against that force that's pushing down to squeeze that layer. So whether it's the materials that are being selected, the structures that are going together, that is key. On the mixture design, it's very important. Again, the rocks and the binder have to be able to work together so you get the compaction, but you also leave enough air voids within the mix. So just saying I want more density without changing the mix may or may not result in more density. There's little things, maybe more rollers that will help it, but adjusting mixture properties and adjusting the percentages of aggregate and the percentages of binder starts all the way back to making sure we get density. In Virginia, we looked at this whole process about 5-6 years ago, and it's been looked at for many years. The goal was to achieve more density in place. And we said we can achieve more density, but you got to have the right mix design, you got to have the right pavement structure, and you have to have the right road bed to place it on to achieve what's desired at the end. So it's not just saying I want more density. There's many different facets that are necessary to meet that goal.
That's good. I like how you brought in Virginia, talking about some actual kind of case studies.
Right.
That's good. So talking about contractors and the use of new technology to ensure good density, can you talk about what contractors are using now to ensure that? What kind of technologies out there available to them, and what are they using?
We're in such a rapid change of technologies available, whether it's with the paving equipment, things that are at the asphalt plants. Today's new asphalt plants have so many innovations built into them to make a very uniform material. So that's a huge investment. We have the additives, we have changes that we can do with the binders. That's an innovative approach that allows us to get better compaction in the field with the warm mix additives. When it gets out into the field, a big initiative, a lot of states, Virginia included, require the use of material transfer vehicles. So when that mix is transported from the plant, gets to that paving site, the first thing that's going through is that mix is going through a remixing approach that gives us more uniform temperatures and gives us more uniform, in case we had any segregation through the load out or through the transport. Once we get that uniform temperature and the uniform gradations, as it's going back to that paver, there in and of itself helps us achieve better density. There's contractors that like to use the Pave IR. While we're not using it routinely in Virginia, it just gives you a good snapshot of, is there anything going on in that paving train before you start rolling it that causes hot spots and cool spots behind the screed? A great QC tool for contractors can be intelligent compaction. While it's not really ready for an acceptance type approach over in the overall QA program, from a contractor looking at using intelligent compaction as a way to monitor their rolling and monitor whether it's just the passes, monitoring temperature, monitoring stiffness, is a good tool to ensure you have good compaction across the mat. So there's a lot of tools. Using non-destructive testing devices is another way to, again, ensuring you got density. By the time you take a core, if that's how you accept it, it's too late. So it's doing all the things upstream from the plant to the design, through the remixing, to the making sure the temperatures behind the screed are uniform and those rollers are doing their job, whether it's through intelligent compaction or other methods, is all necessary. So when that final product, the contractor and the agency has very good assurance that it's going to meet the density requirements set out in the specifications.
That's good. That's really good. Kind of need to keep move on to a different topic. I think
That's fine.
We're running out of time. Good, and I had some questions about intelligent compaction. You've already addressed those. Let's move on to smoothness.
Okay.
Talk about how smoothness is used or should be used in pavement design.
In pavement design?
Yeah.
Ooh, my background is pavement design.
Okay.
That's where I started my career. That's what I did when I was in consulting. When I worked for VDOT for many years, I was on the pavement design side. Incorporating smoothness is more of an expectation than, to me, a design criteria. We put in our specs at the end of the project, it needs to be this smooth, because the traveling public doesn't care if it's red, white, black, blue. They want a smooth pavement. They want a safe pavement. They want a reliable pavement. So from the design standpoint, it's putting the right thickness. We've seen in Virginia, did projects years ago looking at our high-performing routes. They had proper thickness, and they had smooth surfaces. So if we can build the pavement properly, then we should expect on that final surface layer, that surface mix that we lay, that it's got the smoothness so we can minimize dynamic loading, that we can minimize the roughness that does lead to accelerated deterioration in those upper layers. But to work it out into a pavement design, it's got to have the right thickness. It's got to be a perpetual type of design. If it's too thin, the roughness will be built in. Even you can start with a smooth pavement. You don't have enough structure, so as things start moving around, and you see it on a lot of lower volume secondaries, you see them on lower volume primaries, that are not thick enough, that over time, just the type of loading that we see now on our routes causes that pavement structure to deform, build in roughness, and as roughness builds in, it builds in deterioration that accelerates it.
Good. So I was going to talk about, or ask you then, and you touched on it already here, but how does smoothness correlate with future rehabilitation?
The good thing with smoothness and rehab, for asphalt pavements, smoothness isn't usually what triggers a rehab. Most agencies, including the one I worked for, cracking was more the driving force to rehabbing a pavement. Built thick enough, what we're doing is not rehabbing, we're just resurfacing, whether that's a mill and inlay or an overlay. Roughness doesn't fall into, because asphalt stays smoother longer. So that's not a rehab maintenance type trigger in most instances. The wonderful thing is with enough structure where we don't have structural failures and we're trying to maintain a functional surface, a smooth, a surface with enough friction for safety, enough visibility for at night. As those properties deteriorate over time, like a roof on a house, we can go in and quickly resurface it or overlay it to restore it, and we're not looking at a structural expensive fix due to roughness over time starting to fail.
Can you talk about the role of smoothness in environmental sustainability?
For many years, lots of different studies have been done and been part of some of them where the smoother the pavement, the less user cost, vehicle cost are created, less fuel's consumed. With less fuel, you have less pollutants, whether it's fuel from starting all the way back at the refinery or just the fact that the facility that you're on creates through, rougher roads. Fuel mileage goes down, impacts on the cars go up, impacts on the users go up. So anytime as we let our smoothness become rougher, we impact on the sustainability side, because now not only is it impacting the users and it's impacting all the things around it, now we do have to go in more frequently and resurface a road to restore it back. So the longer we can keep that pavement smooth, we can keep the users moving, decrease their cost, decrease the need for natural resources, then we've got a more sustainable product and a longer life product.
Let's see here. How should DOTs use incentives and disincentives to support building smoother pavements?
The use of incentives and disincentives since mid-90s in Virginia. We've had specifications even before then, starting with the California Profilograph. It had an incentive and a disincentive in it. As in the mid to late 90s, Virginia moved to the inertial profiler. We built in incentives and disincentives. Typically, they're always weighted to the disincentive side, but as we saw over time, the more incentives that was provided to the industry, that allowed the industry to make the investments in people which is a huge investment, and the investments in equipment, the investments in technology, because they are looking at it from a business standpoint. I've got to make a profit. And if I can make a profit and be able to get the project and be able to get to the incentive, then at the end of the day, it's a lower cost to the owner, to the user, because they're getting a better price initially. The contractor is still allowed to make money, and at the end, the user benefits because it's longer times between resurfacing because you're starting with a very smooth pavement. So the incentives we've seen in Virginia switch from mainly weighted toward heavy disincentives if you don't achieve it, to those have stayed the same, but there's also now heavy incentives up to 15%. And the contractors are business people that are looking at and say, what can I do to achieve that? Is it investing in the right transfer vehicles and buying a new paver? Is it an extra roller? Is it more training and better training for my people? So it ends up being a win-win for both sides. The state gets what they expect, the users get a smooth pavement, and the contractor is able to make money. And when they all three win, everybody wins. With disincentives only, you're working just to achieve the minimum because there is no carrot to achieve the maximum. And that incentive puts that carrot out there for the contractors to do what they necessary because they're competing. They have to win the work. And if there's 3, 4, 5 bidding against it, the one that can take that incentive into their bidding process and win the job and make money is the one that comes out on that side the best. But everybody wins.
That's good. You know, I've gotten a lot of good responses to that, but I like the way you did it because you phrased it from the contractor's point of view, and did a good job with that one. So let's see here. Let me ask you this: what smoothness value do you understand to be good as industry standards for DOTs to adopt? Are you able to speak to that? That's probably talking a little bit more about specific smoothness numbers. Is that right?
That's what I'm trying. Can you read that again? And
Sure. What smoothness value do you understand to be good as industry standards for DOTs to adopt?
I wonder if that goes back to the International Roughness Index, or if there's, because that's what industry and agency has moved toward. We've moved away from the California-based profilograph. Most states have. The International Roughness Index is the one, starting back with the Road Profiler Users Group that was formed over 2 decades ago to bring DOTs, for the most part, into understanding how road profilers work, what the values mean. Since we've adopted IRI in most states, it's a value that we can understand. It's not a 0 to 5 where you're getting granularity. You know that if you have a 60 inches per mile value, we know that that's smooth. Federal Highway has adopted different roughness values to mean a good, a fair, and a poor pavement. So it gives us, with IRI, a thought in our head that we know that road's 180, we know that it's rough, so it gives us a good feel for what's good and what's bad. But I'm trying to decipher exactly what that question is entailing.
Right.
The big thing is education. When we started using IRI in Virginia heavily in the early 2000s, a lot of work was done to educate everybody, both the industry and the agency, is what do we mean by an average pavement? And an average pavement says you got the smoothness that the owner expects. If you exceed it, there's an incentive associated with it because we know it gives us a little longer life. If you don't achieve it, we're going to get less life out of that pavement surface, so we're going to have to do resurfacing sooner. So educating everyone to know if you can hit a 70 and you're on the interstate, Mr. Contractor, you've met the expectations. If you give us a 90, then there's penalty associated with this. But if you can give us a 45, which is much smoother than what our expectation range is, you'll benefit from an incentive. The agency and the taxpayer benefits from a year or 2 or 3 life. And if you just look at it from simple life cycle or an economic analysis, what an extra year of life will do in terms of agency savings and user savings, it greatly trumps whatever incentive that could be paid on that project to a contractor. But it's education. Why do we want it? Why do we want to pay incentives? Why are disincentives necessary? Because when you look at the bigger picture, agency cost, user cost, anything better than what is expected has great benefits to all involved.
That's good. I like that response. Are you able to speak to MAP 21's smoothness requirements?
I am, but probably not to where I could really answer a question very intelligently. I mean, I know where the different break points are, and that's continued to evolve over time, but if you got me down into the weeds, I've stayed out of the weeds on MAP 21.
Yeah, okay. Let's move on then to long life payments.
Okay.
So what are some key factors to ensuring long life payments?
From the very beginning, if you want a long life payment, it starts with the proper mix design, mix selection, and payment structure. A long life payment doesn't mean it has to be 2 feet thick. We've seen many pavements around the state, around the country, that anywhere from 8 to 12 inches thick becomes a long life pavement. The way they react is different than a 6-inch pavement. But to get an 8 to 12 inch pavement to work properly, it starts with proper construction of the subgrade, treating it if it needs, whether it's a stabilization, needs to be undercut, then it's selecting the right asphalt. You know, initial theory with pavement design was you put your premium materials, your premium binders on the top, then your next lift you can get a little cheaper, next lift you can get a little cheaper, and then at the bottom, all right. But that's completely backwards, because what costs the most to fix? What's on the bottom. I can fix the top easily, but if my base and my sub-base are the source of my failure, now I have created a huge maintenance issue for the owner and the users in the future. So turn it around, start with the proper structures, the proper foundation. When you build a house, you have solid footers. And then as you start to build up and build out, you're not jeopardizing quality. For that long life pavement, it's starting, if you need a high modulus, high binder base layer because you want to keep the air out, you want to keep the water out, you don't want to have problems with stripping, you don't want to have fatigue related issues. It's using that as your base asphalt layer. You're putting the right rut resistant binder layer in there, so it's got the right asphalt properties, it's got the right stone skeleton, it's got the right mixed properties so it doesn't rut. And then just finishing off with that riding surface, that roof on the pavement, that it's got smoothness, it's got friction properties, it's got enough binder in it for durability. All these have to come together in your long life. It's just not designing a thicker pavement. It's designing a smarter pavement with the right materials and not thinking thicker is always better, because there is a point that you have diminishing returns, that you're just spending money that you don't need to.
So it sounds like in some cases that this is really a shift in philosophy.
It's a huge shift in philosophy. The 93 guide from AASHTO let you build it as thick as it would give it to you. It wasn't until a lot of agencies, Washington State really comes to mind, where they started looking at their pavements, looking at their detailed pavement management system, and found, depending on what side of the cascade you were on, how thick was thick enough. And they started looking like 9-inch pavements are working for us. Why would we build something thicker? Even though the pavement design approach may tell you need 14 inches. 9 inches has worked for 30 years. You go to the other side of the mountain range to west of the Cascades, different climate, different traffic levels. All right, you need to be a bit thicker. Again, when you look at it from our conventional design approaches, whether it was mechanistic and straight mechanistic or empirical or a blend of the two, we would still come out with pavement structures that were much thicker based on our design approaches. as we've moved and started looking back, a lot of this was triggered when states were encouraged, if you're going to implement the ME design guide from AASHTO, calibrate. Well, if you go start looking at calibrating and you look at your well-performing pavements and the ones that don't perform very well, you start seeing that what's designed and what's actually performing out in the road may be vastly different. So with these long life pavements and getting the right designs, because it is philosophy, whether it's the stuff that's been done at NCAT on the test track to see what they've deemed perpetual pavements and they've measured responses, really does transfer over to agencies to look to see your design approach may say you need to be 15 inches. But if you look around your state, 11 inches may have been out there for 30, 40, 50 years, and it's performed well. You don't have structural failures. All your work is concentrated on the surface with resurfacing the top 2 to 3 inches of your pavement.
That's great. What's so this is a conference this week is on stone matrix asphalt. What's SMA's role in long life pavements?
SMA for.
Hold on just a second. You got a whistler.
I heard a whistler.
All right, let me ask that again.
All right.
What's SMA's role in long life pavements?
SMA fills the role of that durable, long life surface course, and in many instances, that durable, rut-resistant binder layer, intermediate layer. So when you take 2 layers that are high in asphalt content, so it provides durability, it provides resistance to cracking. You take the stone skeleton, you avoid rutting. So if you've avoided rutting, you've avoided cracking, you avoid losing friction, and it stays smooth for long, then its role in, whether it's an interstate or a long life pavement, is now you've built an asset that instead of expecting to come back in 15 years, it may be 25 years before you go back, and not the pavement and the loading, but the environment around it may have led to the deterioration eventually of that surface where it can just be milled off and replaced. So when you think of SMAs and where we should be using them, high traffic, where anytime you disrupt commerce, it costs money. You know, it's not an agency cost, but it's a global cost because most industries use tractor trailers on our interstates as moving warehouses for just-in-time delivery. So anytime you slow them down or delay them, it has a ripple effect through the economy. So the fewer times that we're out there having to do any type of maintenance, it keeps commerce, it keeps people, it keeps the economy flowing. SMA provides that because on these high-risk, high-priority corridors, these freight corridors, we shouldn't be out there very often. So we have to use premium materials, whether aggregates, binders, et cetera, that's available and it's part of the SMA structure to do that, to achieve, get in, get out, and stay out for a long, long time.
That's great. That's great. I'll tell you what, we're kind of running out of time, so I want to just maybe ask you 1 or 2 more questions.
That's fine.
So again, talking about changing the paradigm of thinking, how does the LLP approach, a long life pavement approach, change the design paradigm? And I think you've already touched on this a little bit, but maybe take a different cut at this question here. So let me try that again. How does the LLP approach change the design paradigm?
The long life approach to pavement design turns the conventional design on its ear. What I mean by that is we have looked at pavement design for so long as bottom-up failure. From the very beginnings, when we started formalizing pavement designs, we were guarding against a bottom-up failure. We expected it to eventually fail from the bottom up. As time has gone on and as materials have improved, as technologies to produce and lay these materials have improved, we've learned that Bottom-up failure doesn't have to happen. We can learn that at some point if we have enough thickness and if we have the right combination of asphalt layers, that our pavements don't fail bottom up. Yet we still design typically for that bottom-up failure, which isn't occurring. So the long life paradigm change is pick the right materials, build it thick enough so the stress strain level at the bottom of that asphalt is not exceeded, that we don't have enough cumulative stresses at the bottom from repetitions, that we have it. Once we've achieved that thickness, and a long life approach may say it's 10 inches, hold everything the same. You do a traditional, whether it's an empirical or a mechanistic empirical, it may say you need 14, 15 inches. But if 10 inches tells us that that's it and that's what experience is, then the change and the impact is 4 inches. If you think about what 4 inches cost per mile to the agency and to the owners and to the taxpayers, if we can save that 10 inches and get the same performance, then think of the other projects that can be performed because we've had so many years of deferred maintenance. The needs greatly outstrip the funding available. 4-inch savings may allow you to do another project, may allow you to do a few other projects. But the long life pavement approach, when you figure out what the thickness is and it's thick enough, NCAT did a study for us. A lot of the country, it's about 14 inches max. You look around the country, you hear about 16, 17, 18-inch thick pavements. That's a lot of money, a lot of funds that's being spent for no benefit. So it's optimizing pavement structure, eliminate bottom-up failure, have the funds that's available, but you got to pick the right materials from the beginning that you end up with a long life pavement.
That's great. Last question I want to ask you is just where do you see the asphalt industry headed over the next 10 years? What do you see for the foreseeable future here?
It's exciting because we're in such a rapid time for change. Some good, some it's going to be the challenge. We have a huge turnover in our workforce. The generations that built this network, that built the interstates, they're retiring, whether they work for the asphalt industry or they work for the transportation agencies. That's going to provide a challenge, but a huge opportunity for doing things differently, whether it's from how we build our roads. I can see more connectivity between the truck that's dumping at the front to the finish roller in the back. So the more autonomy that can be built together to link them all together should have a huge impact on quality, because you don't have now worker fatigue, because you're not going to be able to have that huge number of workers that we were accustomed to in the past. In the next 10 years, those paving crews will be greatly reduced just due to the lack of workforce. You're going to see changes in that workforce. The types of degrees they may or may not hold. You may have somebody that's very good in automation, linking things together. You're going to have specialists at the back that knows how all the equipment works. That's going to be continually changing. We see our binder markets changing. Where we had confidence in where the oil was coming from to make our binders, because of the globalization, that's continuing to change. So there's going to be innovations on the additive side to maximize the performance of asphalt mixes, whether it's adding things such as rejuvenators, more in the warm mix technology, fiber technology. But a huge change that we'll see, especially in urban areas, is more and more focus on the sustainable side. What can we use with all that material that we already have on hand? Tens of millions and billions of tons of material that's laying on our roads. How do we recycle those in to make a long-lasting pavement? How do we take our wrap, our milling piles, incorporate those into new mixes? Virgin products are going to be an anomaly in the future because of the demand for resources. So we have to be smarter on how we use what we have and minimize the amount of new products, the new binders, the new rocks that's necessary to build and maintain the system.
That's great. Is there anything I missed or anything that you wanted to add?
I don't know, this was pretty extensive.
Believe it or not, now I left some questions on the page. I
You
didn't
did?
answer all of them.
Why? No, I believe the biggest challenge that I have seen, and it doesn't matter whose hat you wear, is workforce. In Virginia, we're working extensively with our community college partners to not only just do simple accreditation training so they can work on VDOT jobs, but we realize we've got to be intentional with recruiting the new workforce. Whether that means trying to infiltrate the high schools and the middle schools to help them understand that what you see in this asphalt industry is not that group of men and women standing alongside the road, but there's people that go from that level to all the way to the presidents of companies that are a possibility. So it's opening their eyes to what's available in this industry. It's not just the few people that you see standing alongside the road working, usually in odd hours. It's hot, but it's a type of job that you can get beyond just a living wage. They can make very good money. So the workforce is a huge piece. Safety, the distracted drivers that we see and we hear about every day, every week, not only in the Commonwealth of Virginia, but we hear about from across the country of workers being struck, workers being killed. And it's not because of the drunk driving that we feared 20 years ago. It's everybody with a handheld device, paying attention to the screen on their dashboard, that they get so caught up in those that they miss, whether it's the signage, whether it's the people that's trying to wave them down, and they enter these work zones. And they're people with families that are losing loved ones because of the amount of distracted driving. Last week alone, I knew of 3 different accidents within Virginia, 2 that resulted in fatalities, going back to distracted driving. And it's something we can solve. I'm hoping in the next 5 to 10 years, automation will help us cut down on that. Maybe as we go to connected and automated vehicles, as you get to a work zone, that work zone takes your vehicle over, it slows you down and it keeps you in a straight path so you can get around those workers that are trying to do their job and not having to keep their head on a swivel to keep from being hit. But that is huge. And then as we just continue to approach the next generation of vehicles, the connected and automated vehicles, to make sure that we have the payments in place, the materials in place to allow them to be successful. So that's a challenge that the industry will have to step up to, is saying, what are those products? What does the asphalt in 10 to 15 years have to look like if you've got tractor trailers platooning? You know, we've designed for many years wander into our design approaches, rest periods into our asphalts. If trucks are one behind the other, there's not going to be wander and there's not going to be rest periods. So we need to make sure that the next asphalt will stand up to it for time, or we're not having to get out there with them or frequent maintenance. That's going to be a challenge, but it's also a huge opportunity for our industry and for our industry partners to be innovative.